Our last speaker for this session is Hannah Cleon from the University of California in Berkeley. Her field is in astrophysics, and her advisor is Elliot Quartert, and she did her practicum at Oak Ridge National Laboratory in 2017.
So today I'm going to talk about some of the work I'm doing for my thesis on the multidimensional effects of jets on neutron star merger light curves. This is work that I've been doing at Berkeley in collaboration with my advisor, Elliot Quartert, Dan Kaysen, who's faculty at Berkeley and also staff up at the lab, as well as a postdoc at Harvard, Paul Duffel. So neutron star mergers are what we call multi-messenger events. That is to say that we see signals from them across the electromagnetic spectrum, as well as, and we also see gravitational wave events from them. So you get a neutron star merger by two neutron stars starting off in their orbit close together. And then as they orbit one another, they emit gravitational radiation, which causes their orbit to decay, lose energy, their separation shrinks. And then this continues until all of their orbital energy has dissipated or has been radiated away. We see that gravitational wave signal with, say, LIGO. So as they merge. Then there's a dynamical coalescence phase, which involves, which ejects a few hundredths, maybe, of a solar mass of material, which is then a prime site for the R process, which Chelsea did a fantastic job of introducing for me yesterday. But basically, if you missed that or need a brief refresher, all you need to know for this talk about the R process is that it produces heavy radioactive elements and will be a significant source of radioactive heating, which drives which drives an optical transient called a kilonova. Also, this process, sort of in the first few seconds, launches a jet. Not this kind of jet, that kind of jet. Basically, by jet here, we just mean a collimated relativistic outflow. And this jet, we think, also causes gamma ray emission. And then the radioactive transient, I'll call a kilonova or a macronova. Basically, astronomers are super creative with naming, and it's called a kilonova because it was expected to be about 1,000 times brighter than a classical nova. There was a whole thing in the literature about calling it a mini supernova, but then there were some very strong objections on etymological grounds. So all of this was theoretical, but then came together in 2017 with the first confirmed observation of a neutron star merger. So there was a gravitational wave signal detected by LIGO, shown on that spectrogram on the bottom. That's frequency as a function of time. And then there was also detection of gamma rays about 2 seconds later. Then within the first 12 hours or so, optical and IR astronomers discovered a new transient, discovered a transient, so a new bright source outside of a galaxy about 120 light years away. And this transient was very unusual, mostly because of how quickly it evolved. So this is showing its light curve, so its luminosity as a function of time. And it's in the bright blue. And the white lines, if you can see them, are comparing against other types of stellar explosion events, which generally evolve over much longer timescales. So this was all mostly consistent with the theoretical picture that had been developed over the last, say, 10, 15 years. So the question then is, what's next? And one of the things I'm interested in looking at is what kind of diversity can we expect to see in subsequent kilonovae? Because, well, so for one, we don't expect the mass distribution outside of the final object to be the same, and all of these systems are going to be slightly different. But even at a more fundamental level, we're not going to be at the same viewing angle relative to the orbit of the neutron star, and that will probably at least somewhat affect what we see. So what I've been looking at is what are the effects of different viewing angles on the kilonova signal. And in particular, I've been looking at the effects of shock heating due to a prompt jet plowing through this expanding material that's been flung out in the merger. And I'm also looking at the effects of how changes to the density structure induced by the jet affect the light that we see from these events. So broadly speaking, this type of transient can be powered by there are two possible sources of heating. There may be some others, but the main ones that I'm going to focus on are the potential for there to be a significant signature of shock heating due to the jet. That energy is deposited over timescales of seconds, and this is as compared to the radioactive decay of nucleosynthesis products, which has a similar energy budget of about 10 to the 50 ergs, which, for those of you who don't spend all of your time around astronomers, is 10 to the 43 joules. But the timescale for the radioactive decay is much longer. It runs from there's heating starting at about a second and continues out to days and beyond. And the important thing to note is that all of the shock heating is deposited in the first second into an expanding ejecta. And if you have a hot ball of gas, if you let it sort of expand of its own volition, if you let it adiabatically expand, the total thermal energy will drop off due to that thermal energy partially going into moving the ejecta along. So by the time we see these events at, say, even an hour, which would be really early to find one of these, a lot of the heating from the jet would have dissipated away. And so at very early times, we might expect to see a signature from the shock heating, but at later times, we really do expect this to be dominated by the radioactive heating. So broadly speaking, our approach is to perform 2D relativistic hydro simulations of a jet interacting with an expanding outflow. And we run these for from about 10 milliseconds out to about 100 seconds post-merger. Then I evolve these out using some simple prescriptions out to 15 minutes, which is when I start 2D Monte Carlo radiation transport simulations with a code called Sedona. And I run the radiation transport from 15 minutes out to about 10 days, and I get optical signatures, or I see how the luminosity evolves across the spectrum, across the electromagnetic spectrum, starting at about an hour, and that goes out also to about 10 days. And I'm specifically looking, again, at different viewing angles and seeing how does this look if we're very close to the jet as opposed to if we're just staring at the equator. So here's a movie, just to situate you, of one of these jet-ejecta simulations. There we go. So we have an energy injection at the center, and the jet plows through this simple analytic model for what the ejecta could look like, similar to what the ejecta would look like shortly after the merger. And this is a pretty energetic jet, and so it stays collimated, which is to say it stays at a small opening angle and just totally plows through the ejecta, drastically changing, this is the density, so it drastically changes the density structure and also does change the temperature structure as well, with the jet heating this cavity that it's left. So now I'm going to talk a little bit about Sedona, which is the primary computational tool I use. So it is a parallel multidimensional Monte Carlo radiation transport code, which basically means that we use Monte Carlo methods to solve the Boltzmann equation in 3D. So broadly speaking, the two things that we need to keep track of, and we keep track of them separately, are the background gas, which we follow on a grid. At each cell, we have an opacity, temperature, composition, and radiation field. And I should also note that this opacity is a very strong function of photon frequency. So one, this takes up a lot of space and memory, but this is very important because a lot of the R process elements, and Chelsea touched on this a bit yesterday, a lot of the R process elements have very, very complicated line structures and fairly high opacities. So this can lead to some interesting opacity structure. Though I should say I'm not looking at any of that just yet. I'm currently just using a an opacity that's constant everywhere and also constant in frequency, just to take an initial stab at this problem. We also keep track of, we also have particles, which basically operate like superphotons. They're just like packets of photons. So each particle is associated with a photon frequency, a total energy, and also has a direction that it's moving. So roughly how the code works. So each rank, and this is parallelized with both MPI and OpenMP, each rank has a copy of the grid and some set of the particles. So all of the distributed memory is in the particles, and the grid, everyone has their own copy. Each rank computes the opacities for a chunk of the grid. That gets communicated to all of the ranks. Then there's the step that's currently parallelized in OpenMP, which is where we calculate the mean free path for every photon, and we also propagate and scatter all of the packets. And all of that propagation and scattering is the main part of where this code really is Monte Carlo, in that there's some statistical distribution of how far a particle will travel given its mean free path. We sample from that. We also sample from the distribution of the scattering angle that it can have after different types of electromagnetic interactions. So after all of that's done, which tends to be one of the more expensive steps, we then calculate the radiation field at each grid cell, and then all of the ranks again communicate that to all of the other ranks, so everyone has the same picture of what's going on with the gas. And then there's a gas update step, and then we do it all over again. So Sedona is still under very active development. I recently added capability to checkpoint and restart simulations, which included saving and restarting the random number state, which is particularly useful as a validation check, that if you that if you stop and restart the simulation, you can recover the exact result that you would have gotten if you never did that checkpointing. There's also a postdoc at Santa Barbara, Benny Sang, who recently added doubly diffusive Monte Carlo transport, which will be very useful in these high optical depth regimes where the mean free path is very low, and there are many, many, many scatters that need to happen in the particles for them to get out. So this will hopefully help the performance of the code a lot, especially at early times in these transients. One of the things I'm going to be doing next week is parallelizing the opacity calculation with OpenMP. Currently, it's just the transport. And because of the memory demands of this application, being able to parallelize everything in OpenMP and only have one rank per node will be very, very nice. We'd also like to move towards GPUs. This is something that we've been toying with a little bit. In general, we aren't entirely sure how to leverage accelerators given mostly memory layout issues. So if any of you have experience with Monte Carlo radiation transport or Monte Carlo transport in general on GPUs, let me know. I'd be happy to chat. So back to my science results. So roughly speaking, these are what our input models look like, and these are for different jet energies and opening angles. The important thing to note is that this early model is the one where the jet evacuates the largest cavity. In the wide breakout case, the densities remain a little bit higher. The left panel is density, the right is temperature. And then we also have sort of a control failed case where the jet doesn't actually end up affecting the ejecta that much. So this is luminosity as a function of time, log time since the merger. The darker colors are on the pole of for viewing angles along the jet axis, and the lighter colors are for viewing angles at the equator. And the orange points are the detected kilonova just to guide the eye. And we see that there's a significant brightening on the pole relative to on the equator in the model with the largest evacuated cavity But that isn't necessarily the case in all cases, and also the light curve on the equator is largely the same throughout all of these, and particularly matches all of the light curves in the failed case. And this top row so the top row here shows shows with R-process heating and jet shock heating, and the bottom row is light curves with just the R-process heating. And ultimately, our intuition about the energy budget is right in that the R-process, if you ignore the jet shock heating, the light curves are basically identical. I'd like to thank my collaborators at Berkeley, and also everyone who made my practicum at Oak Ridge a great experience, especially my practicum advisor, Bronson Messer, and also Judy Hill and Jim Hack for making it a very welcoming and smooth experience for me. Thanks.